next one is the gas turbine cycle. Okay. Why do we use this gas turbine cycle? So there are some examples here. So that one example is that electricity generation. Okay, you can see this one is this one is Nakhchivan. Okay, so that you can see that 64 megawatts of electricity is generated by the gas turbine cycle. Okay, this is cycle very similar to diesel cycle that is for the petrol engine, diesel engine. This is another thermodynamic cycle that we use for electricity. And this gas turbine cycle, it's also used in the engines of the airplanes. Okay, the engine of the airplane is the gas turbine cycle, exactly the same one, but you have modifications. Modification means that here that you have nozzle. Okay, but in the real gas turbine cycle you don't have the nozzle, but you are adding nozzle for the momentum, higher momentum that needs to propel the aircraft. And here you can also have different modifications, like you can have the propeller, you can have the expander, diffuser, you can have the diffuser, or you cannot even have any of it. It depends on the configuration, but you have slight modifications to the gas turbine cycle. But then you should know that this is the gas turbine cycle used for the airplanes. Okay. And also you have that Baku CHP, it is that combined heat and the power cycle. This one is combined heat and this one is power. This is again gas turbine cycle. That is this one. You are using to generate electricity of 107 megawatts. But here that electricity generation, so after using the gas, so that some of the gas that leaves the system has high temperature and high pressure. So what we do is that instead of wasting that energy, we are using that energy for heating the households, okay, for commercial heating, district heating systems. Therefore, here you have the combined heat and the power system at the same time. You are getting power from the gas, and since when it leaves the system, for example, you can have a look at the airplane, so that at the outlet, okay, you have high energy. Okay. But instead of wasting this high energy, what we are doing here is that we are using this high energy as district heating. Okay. Also in airplanes, there are some modifications that instead of wasting this high energy, they are using afterburner. Okay. That afterburner is, you know, that uses that this outlet energy and for the aircraft. Okay. Good. And there is one more, that gas turbine cycle. This is Sumgait. Okay, I don't know the power. We can see it. The power for Sumgait is how much? Yes, 525 megawatts. Okay, this one generates 525 megawatts. This is again gas turbine cycle. Okay. Okay, so there is another news here. You can see that. So we have that this one is the combined gas turbine. Okay, so the combined gas vapor cycle. So what it means that here you are using the gas as well as with the water vapor. So this water vapor cycle that is used, it is called the Rankine. Okay, this will be next slide, and the gas part is this slide is used, which we will talk about it. Okay. And another interesting thing here is that I should talk to you for the airplanes. That I think it is before 1930s. I don't remember exactly. Before that years, people were using internal combustion engine. This one was used for the airplanes. Okay, but what happened is that in 1930s, the people have invented the gas turbine. Okay, this one, gas turbine engine, actually, is invented. Okay. So when it is invented, this one has higher power than that one. Okay, this one, gas turbine, has higher power than this one. So therefore, the velocity of the airplanes increased. So it increased the amount that you had the sound, barrier. Okay. So it was the velocity increased the amount of to the speed of sound, which was more than 340 meters per second. This is the speed of sound. And this has become a barrier for the people. It was called sound barrier. Why was the sound a barrier for the airplanes? Because the design of the airplanes was not prepared for that effect that happens when you reach the speed of sound. Because when you reach the speed of sound, the forces change. You have different forces. You have the shock waves, okay, that affects the stability of the airplane. And therefore that high speed, due to invention of the gas turbine engine, was called the sound barrier. It was a barrier that you should overcome. But that at later years, the people have invented new methods to overcome that stability problems near the speed of sound. And the commercial airplanes the commercial airplanes even can fly to the speed of close to the speed of sound, and it is not a problem for today, okay, but it was a problem for the past. Okay, for today, the commercial airplanes can fly at speed of sound. Okay, it's not a problem. Okay, and this was another historical stuff, but the problem has been solved, I think, in 1950s. Okay, it's solved, and they gave a different design to the airplane to solve that sound barrier problem. And now this is the small chart of Azerbaijan energy sector. Okay, you can get it from that official website. It's not a problem. So you can see that this is the maximum power, the maximum power that you get from the Azerbaijan the thermal power plant. But this one used steam. This one used steam, and you have the Janub, which is 780 watts, and the Sumgait 520 watts. For example, this one is the gas turbine. I've said it. Okay, that you can have the Baku CHP, combined heat power, and this one is also that gas turbines. I've talked about this one. So you have the Nakhchivan gas turbine. You can see the name is Nakhchivan gas turbine, 64 megawatts. These are all thermal power plants. You can see it are thermal, and the thermal doesn't mean that it is the gas only. So it can be steam too. Okay, so this one means that it can be steam or it can be gas. Both of them are possible. Okay, these are the range of the power plants. And then we have the hydropower. The famous one is the Mingachevir, you know it, 424 megawatts. Okay, and then you have the Shamkir and Yenichan. And then you have also small power plants, again hydropower, but it is very small, 1.6 megawatts, 1.5, 1 megawatts. And this is the bar chart of the graph. And here I have not included the 1. Okay, 1 is not here. You can see it starts with the 2 because it is very high. This value is very high. It is very high, so that it will, that it will be very difficult to see other power values here if I add this one. Okay. But anyway, you can see the chart and the dominance of the power plants, and you can see that first 5 are very dominant, okay, the thermal power plants. And you can also have this, that is hydropower. You can see 15 is Mingachevir and 16 is Shamkir and the Yenichan. You can see that these 3 also dominates, but the rest is small. These are very small. And overall, in overall range, that Azerbaijan power plant, which is 24 megawatts, okay, and this one makes 36% of overall power production in Azerbaijan. So the sum is 6,713. This is the sum total. Okay. And Azerbaijan is 24 megawatts. This one is 24 megawatts, and this one is the total. And this Azerbaijan power plant, you can see the units, these are megawatts. It makes 36%, which is a very high number. And if you add the top 5, so you add from 1 to 5, this part. Actually here, Shimal 1 and the Shimal 2, they are separate, but they are governed from the same center. Therefore, I've written at 1 power plant, but you should know that this one is different and that one is different. So this power plant, which is that first one, okay, first one, Azerbaijan power plant, it makes 36% of overall that power generated in Azerbaijan. And top 5 TPPs, it means that thermal power plant, it makes 72%. This top 5 makes 72%, and then all of the thermal power plants, all of it, you can see it is from 1 to 14. And all of it makes 83%. What it says is that more 83% of electricity production in Azerbaijan is by steam or gas. Okay, it is not renewable. Okay, you can say that, not renewable. Okay. And the hydropower that is generated by the water here, this one is renewable. This one is renewable. So all of the hydropowers, these are all renewable, and this one is all renewable. Okay, but the rest, which are thermal power plants, are not renewable, and it makes 83%. Okay, and we have also renewable energy in different places for the solar panels, but it's not too much, it's very small. Good. Now, this is the general introduction to gas turbine cycle. Now, what happens in a real cycle? First, let's see it. And as a first stage in the real cycle, you have the compressor here. Okay, compressor. And into that compressor, you have the air. Okay, air enters that compressor, and it is compressed from, let's say, that P1. Let's say this is 0.1 to P2. And you should know that P2 is greater than P1, of course, because it is compressor. And when the air leaves the compressor, it gets into this combustion chamber. Okay. In that combustion chamber, you have the air and the fuel. This fuel-air mixture is combusted. For example, for the airplanes, we are using kerosene. For this one, you can use a natural gas. For example, for Baku, CHP, and this one, NOx1, you can use the natural gas, methane. And for this one, you are using kerosene. So at the end, it is different fuel and the air mixture, and you are mixing these fuels, and in combustion chamber, you have the mixture, and you will have the P3 and the T3. Okay, here you have two turbines. Okay, so that there is compressor, and you have turbine 1. Okay, you have two turbines. Okay, and this turbine 1, it is called that gasifier turbine. Okay, this gasifier turbine, you can see it is connected to the compressor with the same shaft. Okay, so what it means is that whatever power that you get from this gasifier turbine, that power is used for the compressor, because you know from thermodynamics 1 is that this compressor needs work done in, and this gas-fired turbine gives you work done out. This work done out is used to power compressor, and therefore you can see the shaft. This shaft is coupled with the turbine and the compressor, and therefore whatever power that you get from the turbine is used for the compressor. And next you have the power turbine. Okay, this is the turbine that you get power. Okay, and this power turbine is separate, and it is a separate shaft, and from this power turbine you get the electricity. Okay, it is connected to the generator, and from that generator you get the electricity. Okay, and that electricity, I've said it, you have the grid system. Okay, and with this grid system you supply the electricity to different households. Okay, and then from that power turbine you have the outlet. And this one is the real cycle. Okay, the real cycle is this manner. You have the compressor, you are compressing, and the next question could come, why do we compress it? The reason for the compression is that as you compress the fuel and the air mixture, the temperature and the pressure will rise. You will have higher temperature, you will have higher pressure. So this higher temperature and the pressure helps the combustion process to happen efficiently. Okay, instead of mixing this fuel and the air at room temperature, you mix them with higher temperature, and then at that higher temperature, then you have the better combustion process. Okay, so that we are using compressor for better combustion. This is the first one. And as well as you have the higher pressure and the higher temperature, that one is again used to get the power. Here you are getting power from that air and the fuel mixture. Okay, this is the first part. Now comes blast power. Okay, now comes the advantage of the gas turbine cycle. The first advantage is that it has a high power to weight ratio. Okay, so that, however, you can see that the weight of the gas turbines of the airplane, you can see that there are two gas turbines here, one is there and one is there. However, you have two power units here. These two power units have a very high power to weight ratio. This is the first advantage. And the second advantage is that you can have quick startup and the shutdown. This is the next advantage. And the heat exchangers may not be required, which are very bulky in air-breathing open gas turbines. What it means is that why heat exchangers are very bulky. This one is very important part, because if you remember from heat transfer, the heat transfer removed from the heat exchangers are proportional to surface area. Okay. And therefore, if you want better heat transfer, you need larger surface area. Okay? And the larger surface area means that you need bulky systems, for example, these bulky heat exchangers. But for the gas turbine cycle, heat exchangers may not be required. Why it may not be required? Because that, let me go back to here. So the fuel air that comes into that system, you can say air. This air is cold. Okay, and this cold air may be diverted to cool the systems. Okay, it is diverted around the compressor, it is diverted around the compressor, and it is diverted around the turbine blades, okay, to cool it. Therefore, instead of having a high heat exchangers, bulky, very large heat exchangers, you are using air itself, the fluid itself, for cooling purposes. Okay. This is another advantage, and one more advantage is that you have a higher air-to-fuel ratio. Air-to-fuel ratio here is very large. It is about, for example, more than 50. It can be 100, it can be 150. It can be even 200. Okay, we have very high air-to-fuel ratio. For example, this air-to-fuel ratio in car engines, it's about, let's say that 13 to 14. Okay. That you have also stoichiometric ratio, but we are talking about the real ones. So that you can see the difference between air-to-fuel ratio of this one and that one. And since you have the high amount of the air, which is oxygen, okay, and this high amount of air supplied to the system, it means that you have better combustion. Therefore, you have better combustion. And since you have the better combustion, it means that you have less pollutant. You can feel the difference now. For the car engines, you have more pollutant than the airplane engines, because here you have high amount of oxygen and you have a better combustion and you have the less pollutant out to this environment. Okay. And the drawback and the disadvantage of the system is that this is the disadvantage. Okay. Disadvantage of the system is that it is less efficient at part load conditions. And the part load conditions means that, for example, you are not driving the car at full speed, but you are driving the car at part load conditions, at half speed, for example. These systems are not efficient at part load conditions. Therefore, we cannot use it for cars. We can't use it for cars. This is the disadvantage of the gas turbine cycle. Okay, but the rest four are the advantage. And the one more advantage that I can add here is that as you start the system, you have the spark plug here. Spark plug is used for ignition. But as the ignition happens, it will happen continuously. Okay, you don't need to start the ignition again and again. For example, in car engine, you have the spark plug, and that spark plug sparks the mixture at each time. But here you don't need it. As the combustion starts, it will go continuously. Okay. At the end, this is a very advantage. So this is the advantage of the system, that the reason is that it is used. The disadvantages are the reasons that are making the system famous. Okay, now let's see the thermodynamic analysis of the Brayton cycle. Okay, and in the real one, this is the gas turbine cycle, but in thermodynamics, we call it as the Brayton cycle. Okay, this is the thermodynamic analysis. Now let's see what happens in thermodynamic analysis. The first thing is that it is not open, but it is closed. This system here is not open, it is closed. And the second thing is that, and don't consider fuel. Okay. But we are considering air, but the fuel energy is there. Fuel energy is there, but since the air to fuel ratio is more, it's 50, Therefore, that the fuel part is it is not so important. So that m dot of fuel is not so important, it's negligible. Okay? And you have also that third one, it means that frictionless, okay, and adiabatic compressor, and you have the turbine. Okay. Now let's see the T and TS diagram, and you should so that temperature versus entropy. S means entropy. Okay, but you should remember that temperature and entropy diagram, TS diagram, will be used in the next cycles. Okay, in the next lectures, we will use this diagram very often. Okay, this one is very important diagram. Okay, now let's start it. And to start it, I should make it as a closed system. And for that closed system, what I will have is that I have the compressor, okay, and then I have the inlet for that compressor. Let's say this one is 1, and outlet from that compressor, which is 2. And that outlet goes to heat exchanger here. It is the heat addition, let's say, heat exchanger. Okay. And in that exchanger, you have that combustion chamber. You see that instead of this combustion chamber, I am adding the heat exchanger. Okay, here you have the Q in. Let me show it a different color. Okay, here you have Q in by combustion. Okay. And then from that heat exchanger, you go to the next cycle component, which is that this is the free, and then you have that next component, which is the turbine. Okay, and from this turbine, you get the power. But this one, you will give you the power. Work that out. Okay. And this one needs work that in. Okay. And then from that turbine, you will go to back to the heat exchanger again, because I have to make it closed system. And therefore, I should remove the heat. To make it closed system, I should remove the heat. So that I remove the heat from the system, that Q dot out. Or it can be Q out, it doesn't matter. And then you go back to the initial process, initial cycle. And this one will be that 4. You can see I start from 1 and compress it from 1 to 2, and then 3, and then 3 to 4, and then 4 to back to 1. Okay, and this is the first important stuff. And the next important stuff here is that I have forgot to tell you, it is the pressure ratio. Okay, I've written here to remember it, but I forgot it again. So that pressure ratio is that P2 by P1, okay, and that is the pressure ratio, which is PR. Okay. That pressure ratio is the change of pressure from the compressor inlet to compressor outlet. Okay, this pressure ratio, this one affects, that is efficiency. Okay. So what it means is that the low pressure ratio, low PR, low PR and or high PR, okay, is not okay. It is very similar to that is compression ratio in car engines. You should have the medium PRs. So the medium PR values for the gas, the Brayton cycle. Okay, so let me write the medium PR values here. So let me see if I can find it. But you can look at your book. You can see that the medium PR ratios is that from 11 to 16. But it changes due to application. But you will have the medium, which is 11 to 16, to the efficiency. Okay, the medium PR values is okay, and it is from 11 to 16. This is the first important stuff. Another important stuff here is that I also forget to add it. This one is the back work ratio. Okay. What is back work ratio? That back work ratio is that, I've said it, some of the work output, you can see that some of it is used for the compressor. Okay. Back work ratio is that the compressor work that in, the work used to drive the compressor divided by work that out total. Okay, but this ratio, the work dot in that is used to drive the compressor, is a proportion of the total work dot out of the turbine 1 and the turbine 2. Okay, let me write it one more step here. Work dot in divided by work dot out, that turbine 1 plus work dot out is turbine 2. This ratio is the back work ratio. It can be 40%, it can be 30%, it depends. But at the end, you should know that higher the amount of the back work ratio, the worse is your system. Because higher back work ratio means that whatever power that you are getting is used back to drive your system. Okay, this one should be small as possible. Okay? But in reality, it will not happen because you have to get some power to drive the compressor. And you will see next slides how do we minimize this back work ratio. Good. Now let's plot the TS diagram of the cycle here. But you should remember that frictionless adiabatic compressor and the turbine. Now let's start. From 1 to 2, which is the compressor stage. Okay, 1 to 2 from the compressor stage. I will start 1 as here. Okay. And from compressor, the temperature increases, pressure increases. Okay. And I can write it here. T2 is greater than T1 and the P2 is greater than P1 because compressor adds energy to the fluid. So, but the entropy is constant because it's frictionless and the adiabatic, S is constant. Okay. Therefore, I will go in that manner. Okay. This is 2. So let me draw it again because now it seems that. But it should be the vertical. Okay, it should be vertical because the entropy is constant. These are the assumptions. Okay, in reality, it is not isentropic, but you can see that we will do examples where we don't consider the isentropic case. And then from 2 and the 3, you can see that you are adding heat. As you add the heat, let me add this one. S1 is same as S2. This is the first part. And the second one, from 3 to 2, you will have the increase of temperature because it is heat combustion. It is combustion process. But here the entropy also increases because you are adding heat, and S3 is greater than S2. And therefore, you have the increase of the temperature as well as the increase of the entropy. You can see entropy increases and temperature increases. And you have stage 3. Okay. Now comes that stage, but you should remember that I should add that to 4. Heat exchangers is adiabatic. Sorry, that is not adiabatic. It's actually adiabatic, but for the environment, but for the system it is not. But heat exchangers is isobaric. Okay. The pressure drop is not considered. Okay, heat exchangers. In heat exchangers, these are very essentials. Okay, these are used in all of the cycles. In all of the cycles, what we begin with is that the frictionless adiabatic system, the expansion compression process, and isobaric heat exchangers. Okay, now let's do that one. So that P3 is same as P2. Okay. Now comes 4 to 3, and when you go from 3 to 4, you are using energy of the fluid. Therefore, its temperature should drop. Its pressure should drop, but its entropy remains constant because it is frictionless and adiabatic. S4 is same as S3. Now I will go down, temperature should drop. Let me show with arrows. I will go downwards, but the entropy remains constant. Entropy doesn't change. Okay, I reach some point here, and this one's 0.4. And then I'm going back to 4 to 1. Okay, and the 4 to 1, the temperature drops, entropy drops because you are giving off heat, and also the pressure is same. These are the cycle. Okay, let me do that, dear friends. I couldn't catch the 1, so I should put 1 here. Okay, so that is the cycle in thermodynamic analysis. Okay. This is the Brayton cycle. If you have questions till now, you can ask. Otherwise, I'm moving next part of the slide. Do you have any questions? So if I go back to the first page, can you see? Let me show that if you can see. Yes, you can see this. That is the tubes here. Okay, these are used for the stack gases. So as you burn the fluid here, that is fluid and the air mixture. You have this, that fluid gases or stack gases that leaves the system. Combusted products, you can see. Okay, now minimizing compressor work. Okay, so why do we minimize it? Minimum compressor work. So why do we minimize it? The reason is that back work ratio. Because I've said it, that the work of the compressor divided by the work done of the turbines. Okay, this ratio should be minimum because you have to give electricity. You don't need to drive compressor. Therefore, to get the minimum compressor work, what we will do is that, so we will try to find how can we minimize it. If you look at the chart here, so I've calculated the new dP term. Okay, I've calculated this term for the compressor. So what should I know? I should know the relation between the specific volume and the pressure to get the minimum work. It should be minimum compressor work. And so what I can do is that I can say that P nu to the power of n is constant. This is my first option. Okay, if it is constant, n can be, for example, so to find the relation between P and the nu. So P and the nu relations. I can say that P nu to the power of n is constant, and I can take the n value as 1.1. I can take n value as 1.4. I can take n value as 1.5. Or I can say that the process is isothermal process. Okay? And since the process is isothermal, you will have that P nu is RT. Okay? And since the temperature is constant, this one is constant, that one is constant, it will be constant. Okay, and therefore it is the second part where you will have the constant process to find the pressure and the nu relationships. Or you can use the third one, which is the famous one that we are going to use, and intercooling. What is intercooling? It says that instead of that, let me first see these two options, and this one is you can see the charts here. If it is polytropic compression, polytropic means that this relationship is called polytropic relationship. Okay, this relationship is called polytropic relationship. For the polytropic compression, n is 1.5. You can see that chart here. And for the polytropic compression, n is k. You can see this one. And the polytropic compression n is 1.1. You can see this one. Okay. What happens is that, so we are trying to find nu dP. What is nu dP? It is the area. So this one is the pressure and this one is the nu. It is the area under these curves. You can see that. This is this area. You are trying to find the area here. Okay. This is the area. And you can see as I decrease the n value here, I get the less amount of area. I get closer to the left axis. And you can see it here for work of 1.1, you have this amount of work. If it is K is 1.4, you have this amount of work. If it is 1.5, you have this amount of work. And the first thing is that if you drop the N, you get lower work. If you drop the N, you have the lower work. And when it is isothermal, and this is the minimum. Okay. This is the minimum work that you can get from the compressor. But in reality, what the people do is that instead of doing the process as isothermal, because it is impossible, you cannot get the isothermal process. It is impossible to get the isothermal process. What we are doing is that we are intercooling. What is intercooling? Intercooling is that, so the compressors, you know that, let me go from the opposite part here, that compressor compresses the air or the gas to some pressure. Okay, say that from P1 to P medium. Medium. Okay. Medium, it compresses it. And then you cool the system. So here you are cooling. Okay. and then it compresses again. You can see it here. So you are doing compressor in 2 stages, compression process in 2 stages. In the first stage, you are compressing from 1 to a medium range, and then you are cooling the system, and then back to another final state. Okay. So let me show here in one slide. Say that you have the compressor 1 here, compressor 1, and you have P1 to that compressor, and you have P2 to that compressor. And the P2 is greater than P1 because you are compressing it. And let's say that P2 by P1 is 8. Okay. Now, instead of compressing it in one stage, what you are doing is that you are adding 2 compressors. Let's say that compressor 1 is here, and you have another compressor 2. Okay. And what you are doing is that you are compressing again from P1 to, let's say that P medium. Okay. And here the temperature rises. Okay. T medium is greater than T1. And next, what you are doing is that you are intercooling here, so this is inside a heat exchanger. This is heat exchanger, and here you have also cooling water. So this is cold water. Okay, and then as you cool the system, what you will have is that the temperature here, let's say that this one is that T2, okay, and the T2 will be the same as T1, and the temperature drops to the initial value, which is T1. Okay. And then what you are doing is that you are compressing it again. So the next compression stage, it goes to P2. Okay, so you have compressed from P1 to medium range, and from that medium range to P2, but in the between you have the cooling process. You are cooling the system to the temperature 1 value, okay, which is T2 will be the same as the T1 value. This is the intercooling, and we are using that. This is very often used in industry, and here you have that 2-stage compressor, compressor 1 and the compressor 2. And the P2 by P1 is 8, and similarly here it is P2 by P1 is 8. It is the same. But here P2 by P medium is same as P medium by P1. Okay. And therefore P medium will be same as square root of P1 into P2. That is for the Brayton cycle with intercooling. This is the first thing that we are doing for minimizing the compressor work. So another thing, let me do that one and the finish. So we are adding the regenerator. So what is the regenerator? Now let's talk about this one. So this is for efficiency increase. Okay, we are increasing the efficiency by minimizing the compressor work. This is the first thing. And the second thing is that you are using the regenerator. So how do we use the regenerator here? So now let's see that one. So you have the compressor 1 here, okay, and this compressor 1 sends fluid to this one is the combustion chamber. Okay, this one is the combustion chamber, but here you can see the differences. From compressor 1 to combustion chamber, you have another component here. This component is called the regenerator. So how it works? The system works like this one. So you have the compressor 1, and this one is a turbine. The outlet of this turbine, the outlet of this one, is sent in that manner. You are sending the outlet of the turbine in that way. And this one is a heat exchanger. Regenerator is heat exchanger. Okay, and the outlet of the turbine goes through that regenerator or heat exchanger, and the compressor 1 outlet also goes that regenerator. And since this one is hot, it gives its energy to the incoming compressor fluid. Okay, and therefore, if it was T1, now here it becomes T2, and the T2 is much greater than T1. Okay, you are helping compressor. You are increasing the energy of the compressor by adding regenerator here. So you are adding regenerator and increase the temperature of the compressor outlet. And then you have the combustion chamber, and then you have this regenerator turbine. And then from turbine outlet, you are getting back to the regenerator and then outlet. So if you summarize here, to increase the efficiency, so we have done 2 steps. First one is that minimum work compressor. So you are minimizing the compressor work. And how do we minimize it? We are using intercooling. This is the first stage. And the second stage, that second thing that we are doing is that we are using the regenerator. Okay. By using regenerator, you are diverting the outlet of the turbine to the inlet of the compressor by a heat exchanger here. And that energy of the outlet of the turbine is given to the compressor one here. And then combustion chamber comes. And the one more thing that is done for increasing efficiency, this one is the regenerator, intercooling, and you are using reheater. Okay. Now, what is reheater? Let me talk about that one and finish the lecture. So the reheater is that. So this one is the compressor one. This one is the intercooler. This one is the compressor 2. And then you have the regenerator. You can see it. And then combustion chamber here. And then turbine 1. This one is the turbine 2. You can see the turbine 2 goes back to the regenerator, and this regenerator gives energy to the compressor 2 outlet. Okay. Now comes the reheater, and the reheater is that, let's say that this one is the 3, and this one is 4. Okay. Temperature of the 4 is less than temperature of the 3. It is due to that because turbine uses energy. Turbine uses energy of the fluid, and therefore the temperature 4 is less than temperature 3. And here you have the reheater, or you can say that additional combustion chamber. Okay, so that here with this reheater, you are reheating the system to T4 to the same temperature as T3. Okay, you get the same temperature back again. And then you are using in turbine 2, and you get more work output. But the disadvantage of these systems for the reheater, intercooler, and regenerator is that they are having some mass, weight. You are increasing the weight of the system, okay? And therefore, in some part, you are gaining from the power, you get more power and you get more efficiency. But on the other hand, you are getting more weight. And more weight is not good, because that these gas turbine cycles, that these are very low weight energy systems. Okay, therefore there are also portable versions of these gas turbine cycles. It is portable. Therefore, if you add components, it becomes very a massive bulky system. For example, for airplanes, it is difficult to carry these systems. Okay, it will be very high weight. Okay. Therefore, in one part you are gaining, but in one part you are losing.